Hey everybody, welcome back to the Blood Bank Guy podcast. This is Joe Chaffin. It is March 2012, and I am really excited about the podcast we're going to do today. Basically, ever since I started the Blood Bank Guy website way back in 1998, people have asked me off and on if I would do something about antibody identification. The process of antibody identification can be intimidating for people that are just learning how to do it. And I think just about every pathology resident who hasn't done a bunch of them goes into the pathology board examination really concerned about, I hope there aren't too many panels. And that's true for students of other blood bank specialties as well. So what I want to do today is just take you through the basics, just the nuts and bolts of this is how you look at a panel, this is how you approach a panel, and this is in general the basic way that we attack one of these things. Try and take some of the mystery out of it and make it somewhat simpler. There will be a part 2 to this podcast, which will go over some basic case examples. And down the line, we'll go through some more complex cases and more interesting stuff as we move forward. That'll be a separate podcast, a third separate podcast that'll happen in the coming months. But for today, what we want to talk about is the specifics, the nuts and bolts, as I said. One thing before we get started, normally those of you that visit this website and look at these podcasts will know that I typically do a really detailed handout to go with every podcast that I do. In this particular case, this is more of a show you kind of thing than a tell you kind of thing. So while I've given you a handout that just includes the slides that you're going to see today, I haven't given you a specific detailed handout. You can read details about how to do antibody ID in multiple different textbooks. So I'm not really about that today. I really want to just show you stuff and hope that it's useful for you. So with that being said, let's move along. Here's what we're going to do today. The prerequisites we'll cover first, and that'll be just a brief mention of the first 2 parts of the Basic Immunohematology podcast. This is actually part 3 of the Basic Immunohematology series. We'll go over the geography of a panel and do the antibody ID method. As I said, part 2, which will come later, will include case examples and going through some specific cases and how to handle some specific cases. In general, the overview, the blood group overview is that was actually part 1 of the Basic Immuno podcast series. It was in December 2011. I would urge you to check that out if you have not already. The same thing is true for the pre-transfusion testing podcast, which went over testing methodologies and the antibody screen principles. And that was a podcast from just last month, February 2012. So both of those it's essential that you know the information that's in those before you do this podcast. And if you know it already, that's totally fine. But if you haven't listened to them, you might want to check those out. Those podcasts, like this one, are video only. So for those of you that have asked me, when is the MP3 coming out that I can play on my MP3 player? Well, there won't be one because these are more show me things than they are tell me things. We'll do the audio, resume the audio podcast down the line, but for now these are just video. All right. So when do we do an antibody identification? There are really only a very few situations, surprisingly. Obviously, following a positive antibody screen or a positive antibody detection test, we will do an antibody identification. Now that includes if the antibody ID is positive for a patient, on a prenatal visit, for a pregnant mom, or for a blood donor. In either case, any of those cases, we work up the antibody generally through the use of the antibody identification panel. In addition, you also have to do an antibody ID when testing suggests that there's a new antibody in town. In other words, if someone has a history of an antibody, in general, you don't have to necessarily do a lot of work to reconfirm that, though if there is the suggestion of a new antibody on testing, then you definitely need to work that up. And the last one is what I kind of just mentioned. You according to your facility's operating procedure, you may need to do antibody ID to confirm a previously identified antibody. And in many cases, that's done with just very select cells and just looking specifically to confirm or refute the presence of that particular antibody. A couple of definitions that I think you're already aware of. An alloantibody is an antibody against red cells of antigens of someone else's red cells, while an autoantibody is an antibody against your own red cell antigens. Pretty simple. We'll talk about allos primarily today, alloantibodies today, more on autoantibodies in the advanced antibody ID podcast coming down the line. So what is a panel? It's really just an expanded antibody detection test or an antibody screen. That's all it is. Antibody detection tests are generally done with either 2, 3, or 4 cells from group O blood donors, and those donors are fully phenotyped, and you test the patient's serum or plasma against those 2, 3, or 4 red cells, and you see if there's any reaction. If there is reaction, then you have to identify the antibody. Well, the antibody identification panel is simply an expansion of that antibody screen up to from 8 to 20 different donors. It's less commonly 8 and more commonly in the range of 10 to 14 or so, but it can certainly be more. Again, you utilize the patient's serum or plasma. You have multiple phases of testing, as we talked about in the last podcast, depending on whether you're using tubes or gel or solid phase. You have immediate spin 37 and the anti-human globulin phase if you're testing in tubes, while if you're in gel or solid phase, by definition, you are only doing the anti-human globulin or indirect antiglobulin test phase. The reactions are documented on a sheet that outlines every red cell's phenotype, and basically that's all a panel is. When you look at a panel, it's just a documentation sheet that shows all the phenotypes of all the red cells from all those different donors and the reaction of your patient's serum or plasma against those donor cells. More on that in just a second. So let's take a real close look at a panel. It's really important that you know your way around one of these things, and you get less intimidated the more you understand the roadmap. There are some variations, and what I will show you is just a generic panel. It's not associated with any particular company, but this panel will give you a basic idea so that you can handle basically any company's panel that you see. So here's how it is. Ta-da! Here's an antibody panel. This antibody panel has a couple of very specific areas that we need to look at and you need to get comfortable with. Let's start on the left side of the panel and let's take a look at the individual cells. Okay, so going down in a row are a listing of cells 1 through 11 in this particular case. Right next to that is the RH genotype of those particular cells. And you'll notice those are in shorthand, and more on that in just a second. So basically what we have is a series of 8 to 20 group O donor reagent red cells. Let me reemphasize, these are blood group O donors. By definition, the donors on a panel are people that we don't want to be, we don't want to have any ABO interaction. In other words, if someone is group A and they have their naturally occurring anti-B, we want to take that out of the equation because we want to see non-ABO antibodies when we're looking at a panel. Again, this is we mentioned already that you have the RHHR modified Wiener RH genotype for the donor. There's a review of what those shorthand terms stand for. We're not going to take any time to go through those again, other than to say, remember that the 4 most common of these haplotypes that we see are big R1, big R2, big R0, and little r. Important to remember that. Obviously, these panels include cells of different types than that, but those are obviously the most common ones that we see on a panel. You'll also see some other stuff, sometimes on this side, sometimes on the other side of the panel. Typically on this side, you'll see a donor identification number. I haven't showed that on this panel. That's okay. And in many cases, you'll see a special antigen type. That can be stuck on in an additional column on this side of the panel. More commonly, it's found on the other side of the panel. Where you see, for example, that the donor from cell 11 is positive for the Colton B antigen. Okay, important to know. In addition, it's important to know that the bottom row, the bottom row of a panel is typically reserved, it's usually left blank by the manufacturers, and it's reserved for the patient phenotype. Phenotypes are used at the end of this process. We'll talk about them later, but basically that's a place where you test your patient to see which antigens your patient has present. And you'll see something that looks kind of like this. In this particular case, this particular patient was positive for big C antigen, that's the first plus, negative for big K antigen, that's the second blue 0, and then on the far right on the bottom, positive for the Duffy A or FYA antigen. Again, more on phenotyping as we go along. Let's move up to the top of the panel now, though, and let's take a look at what we see. So if you look across the top of the panel, you'll see a listing of different blood group antigens, and these are, for the most part, important red cell antigens because the antibodies against them can cause significant things. This is not universally true. In fact, some of the things that are required to be on a panel or on an antibody screen you see listed up there at the top, and some of those are generally completely insignificant, such as Lewis A, Lewis B, M, N, and P antibodies. But that being said, they are required to be there, and you'll see them on the panel down below. In addition, most panels will have some additional stuff that are some additional antigens that are going to be there that don't necessarily make a lot of difference and aren't necessarily all that important, but they are there. If you take a look at some of these like F, CW, XGA, KPA, KPB, etc., I really want to call your attention to the ones that are either very high frequency or very low frequency, such as the low frequency ones include things like CW and V, which you don't see on this particular panel, but you'll see on some of the panels as we go along, KPA, JSA, Lutheran A. All those are very uncommonly even present on an antibody panel. So in general, we have some decisions to make when we can't rule those out as part of the antibody profile. More on that in a minute. On the other hand, there are some high frequency ones that are there in virtually every cell, such as JSB and KPB, for example. And those can be ruled out in the vast majority of situations. So again, very important to recognize that. Also important to know that in some cases, especially when you're looking at panels from some of the newer manufacturers in the market in the United States, it can be difficult to find licensed anti-sera, especially to some of these high-frequency antigens, such as KPB, for example. So you may see something that looks kind of like this, where you actually have asterisks there instead of pluses. You assume that all of them are positive because that's generally true, but you don't know that for certain because they don't have the anti-sera to test it. All right, moving along, let's look now at cell 1. Now, if you look across in the row on cell 1, we already know the patient's Rh genotype, as we already said. Every plus means that the patient has or is displaying that antigen. Every 0 means that the patient is not displaying that antigen. Okay, so you move across, and basically what you're seeing is the full donor phenotype. You're seeing the D phenotype, this big C phenotype, etc. as you move along. You move down to cell 2, and the same thing is true for the donor in cell 2. Again, you see what's there and what's not there. In addition, you can look at this a slightly different way. You can look at things in columns rather than in rows, and you can see that the donors in cells 1, 2, 3, and 4 are positive for the D antigen, while the donors in cells 1, 2, and 5 are positive for big C antigen. So again, just different ways of looking at the panel just to help you kind of map your way around. Let's take a little closer look at something that's really important for you to recognize, and we'll do that by focusing in on the KID blood group system. The KID blood group system generally has two antigens present on the panel, or the donors are phenotyped for two KID antigens, I should say, the JKA and JKB antigens. And let's take a look at those. So the donor in cell 1 has the presence of JKA antigen only and not JKB antigen. Generally, what we assume when we see that is that individual has what we call a double dose of JKA. Fundamentally, we're inferring what the donor's genotype is by looking at the phenotype. In other words, we're saying, okay, this person has only JKA, no JKB, so it's likely that he is homozygous for the JKA gene, and as a result has a double dose. In other words, two genes and for the same antigen, leave you with more antigen on the surface. Okay, very important concept to recognize. On the other hand, cell 2, you clearly have a single dose of both JKA and JKB. It's obvious that this person is heterozygous, has one JKA gene and one JKB gene. And on the other hand, cell 5 is a scenario where you would assume that this individual has a double dose or is heterozygous for JKB. That's not always true, however, and sometimes this can be difficult for students to get a grasp on. So let me just show you what I mean by this. Okay, so here's the first cell that we're going to look at is cell 1, and this is illustrated on the left side of the image. Again, all we see on the surface is the presence of JKA antigen, so we assume that this particular person is homozygous genetically for JKA, and that is probably true, but it's not necessarily true. If that weren't the case, for example, if there were a null gene for JK and not a JKA gene there, then you would expect to see about half the amount of antigen that I'm showing on the surface. So again, what's important, because some antibodies only react against a double dose of the antigen, and that's called dosage, it's important to understand that we're assuming that this person is homozygous and has a quote-unquote double dose in cell 1, but it may not be true. In most cases it is. Cell 2, it's obvious, again, a single dose of each. You know what the genotype is, and you have an amount of both JKA and JKB on the surface. And finally, cell 5, again, we're assuming homozygosity for the JKB gene with resultant double dose of the JKB antigen on the surface of the cells. Now, again, let me caution you that this is not always true, particularly in blood group systems like the Duffy blood group system. So if we see someone who only is displaying Duffy A on their red cell surface, in other words, you would see a plus for Duffy A and a 0 for Duffy B in that particular donor, you assume that what you have is the situation on the left, that that individual has a double dose of Duffy A. However, as I said before, if they have a null gene, which many African Americans have, in fact, the majority of African Americans have a null gene for in one of the at least one of the loci for Duffy, then actually all you have on the surface of the red cell is a single dose of Duffy A antigen. So it's important to recognize that we assume that we're seeing double dose, but we may not necessarily be, and you have to pay attention to that when you're doing your workups. Okay, enough on that. Let's move on and let's look at the far right side of the panel. And the far right side of the panel is hugely important. There's a lot of things you can learn just by looking at these yellow cells I've highlighted in yellow up at the top. Basically, what you see in these cells is the phases in which we're doing the testing. And in most cases, when you're doing tube testing, you'll see something like this. You'll see IS for immediate spin, 37 for 37-degree incubation, and either AHG or IAT for anti-human globulin or indirect antiglobulin test. They're saying the same thing. Then you'll see a bunch of reactions cruising along on the right side of the panel. And again, there's no question that this is tube testing. You see immediate spin in 37 as well as AHG. It's clearly tube testing. Now, what you don't know from this, just by looking at it, is what the enhancement media is that's being used. There are a wide variety of things that are available. Low ionic strength saline or LIS could certainly give you this kind of a pattern. It would look just like this. So would albumin, so would saline. But the one thing that's very important to recognize is that if you're using polyethylene glycol or PEG as your enhancer, it will not have this kind of a pattern, or it shouldn't have this kind of a pattern, because PEG, as we mentioned in the pre-transfusion testing lecture, PEG will cause non-specific reactions at 37, and you should not include a 37-degree read when you're doing PEG. So either LIS, albumin, or saline, but clearly tube testing. Okay, so that's that one. Now let's look at the next one. Here's a different example from a different case, which has only immediate spin and AHG. Again, that immediate spin kind of tips you off that this is clearly tube testing. However, without the 37-degree phase, this is often PEG testing, PEG being used as the enhancement agent, but it could also be LIS or albumin or saline in a lab who's decided that we don't want to read at 37 because we don't think it's that important. And that certainly happens. So, okay, definitely tube testing, most likely PEG, but could be other stuff as well. Now, here's another pattern. We've got AHG labeled at the top. We only have one column of testing results. This could be one of three different things. This could be tube testing. There's no question about it. And if it is tube testing, here's how you could tell. If you take a look down the right side of the panel here, what you'll see is these check cells that I'm showing you. And we had these check cells on the other panels as well. But the check cells basically indicate that this is liquid testing, that when you had a negative anti-human globulin test, you've gone on and done a Coombs control, as it's called, and it's turned up positive, showing you that you did your reactions proper, or you did your mixtures properly, basically. You see that, you've got tube testing. So that clinches it for you. If you don't see that, then, and you don't see anything else at the bottom, then typically that'll commonly be gel testing. It's not always by any means, but it certainly is likely to be gel testing in that scenario. Solid phase testing, on the other hand, has one characteristic feature, and that's that if you look at the bottom of the panel, in virtually all situations with solid phase testing, you'll see a positive control and a negative control, and they should look like that, with a strong positive on the positive control, a 0 on the negative control. If you see that, that is virtually always solid phase testing, because that's characteristic of the solid phase reactions and what the company puts on those panels. Okay, important to recognize that. Now, finally, if you see nothing at all, if there's no label up at the top and you just have one column of reactions, that is almost always either gel testing or solid phase testing. Labs which use gel and solid phase will very commonly not label that one panel that's positive because they know that it's AHG because they're using gel or solid phase. Again, it could potentially be tube testing, but it's less common for labs that use tube testing to not label a column when it's only AHG. Okay, and then finally, the last thing that we need to take a look at, and is very important to look at in the geography of our panel, is the AC, or the autocontrol. The autocontrol sits down here at the bottom right of just about every panel. It's in a slightly different location in solid phase because you have to have that positive and negative control in there, but generally it's going to be down in the bottom right, and you want it to show a 0 because of the fact that if that is not 0, that indicates that the patient's own serum is reacting against the patient's own red cells, and essentially it calls everything else into question. If the autocontrol is positive, everything else that you see is a suspect reaction, and we have more work to do. We're not going to hit a lot of autocontrol positive stuff today. In fact, we're not going to hit any of it right off the top, but that will come in the Advanced Antibody ID podcast down the line. Here's my best advice to you. You really have to have a plan for attacking these things. If you do things the same way every time, you're much less likely to do something dumb and miss something obvious. It's really important to develop whatever system you're comfortable with developing. There's a lot of systems that are available, that are published and written out there. I'm going to show you mine. Mine is based on a hybrid of a lot of different things, and it includes the way I was taught back when I was in the Army at the fabulous Walter Reed Army Medical Center. Shout out to Walter Reed, hello. But it also includes things that I've learned along the way. I'll show you some variations, but again, whatever system you're going to use it, and use that same approach every time, and try not to be taking a scattershot approach even when you're on an exam. Very important. All right, so here's my approach. The general process that I take is the first thing I do is check the history, and I think that's hugely important. It makes a big difference. We'll talk more about that in a minute. We check the autocontrol, look at the general pattern, look at what's not there to do our crossouts, look at what is there to do our rule-ins, and use special techniques as necessary, and finally ensure statistical significance. There's not a lot of steps, but there are some complexities to those steps. Let's start first by talking about checking the history. That's the fact that we need to check the history is true both in real life and on exams. History can really keep you out of doing something silly. And there's a wide variety of things. We'll talk about some of those on the next slide. But up to 70% of cases, according to some studies, are impacted. Your approach and your interpretation are impacted by what you read in the history. So don't just skim over it. Look for clues, especially on exams. Sometimes they give stuff away. Clinical history examples include anti-D in a pregnant patient. You want to consider RHIG in addition, obviously, to her forming her own anti-D. If someone has a recent bacterial infection, think about antibiotics, potentially inducing a warm autoantibody. Recent viral illnesses, consider autoantibodies like autoanti-big I or little I. If someone's been recently transfused, that's a big, big clue that you need to look closely at the autocontrol. Consider a newly developing antibody. Consider a delayed hemolytic transfusion reaction. Finally, ITP is something that you should know about, because one of the treatment forms for ITP is to use IV anti-D or IV Rh immunoglobulin in patients who are D positive. So you can see D positive patients developing anti-D out of the blue, seemingly, and the reality is that they've just gotten an intravenous RHIG injection. The one thing I didn't put up here is intravenous immunoglobulin, which is also important and has been associated with unexpected antibodies, including anti-A's and anti-B's that shouldn't be there, as well as other antibodies that shouldn't be there in addition. Be careful here. So don't turn off the podcast. I'm not suggesting that we do racial profiling. I'm saying we consider racial profiling in a good way. And what that means is understanding the person's race and knowing the person's race can sometimes help point you in the right direction. And that includes African Americans who lack many Duffy antigens, Asians who are almost always D negative, as well as many Caucasians who may lack multiple high frequency antigens, and that can be a problem when they develop antibodies against those. Finally, consider the serologic history if it's known. Don't rely on it exclusively. If you know someone has an antibody, that can help guide you. If you know someone's phenotype, that can help guide you. you. But be careful. The other thing that I didn't put on this slide, that you need to be really careful of someone who has been transfused within the last 3 months or so in terms of additional work that you may want to do on them for phenotyping. If you want to phenotype someone who's been transfused within the past 3 months, their phenotype may not be their own, and you may have to do some specialized techniques such as harvesting reticulocytes, but more commonly nowadays what people are going to is just doing molecular testing to try and tell what their genotype is and predict their phenotype as a result of that. All right, so moving along, after we've checked the history, the first thing that I always do, every single panel I look at, is I check the autocontrol. The autocontrol being positive changes the entire approach to the panel. Now here's a panel that we're going to beat on for a little while here. With this particular panel, the first thing that I always do is I look down at the bottom, I look for the autocontrol, I make sure it's negative. As I said, if that autocontrol is positive, it leads to a wide variety of things. We'll hit that more with a future podcast, but preview, the two things that we always ask is the DAT positive if the autocontrol is positive? Because the DAT being positive suggests that there is something real and immunohematologic going on. Second, what's the patient's history? Because that can often give you a big clue to why the autocontrol is positive. Those possibilities include the things that you see on the screen. The autoantibodies, both warm and cold, or recent transfusion with or without a delayed hemolytic reaction, drug-induced issues, passively acquired antibodies. Again, this is just skimming the surface, and we will hit more on this later on. So after you've looked at the autocontrol and hopefully ensured that it is negative, let's move on and look at the general pattern. What are we going to learn from looking at the general pattern? There's really a lot that you can learn. It can really help guide the way that you're going to look at the panel completely. First thing you want to see is, are those reactions uniform or variable? Second, are they against all, most, or just rare cells? And finally, what phases are those reactions present in, if there are phases available in the testing that you're seeing? And let's take those one by one. The variability, certainly uniform reactions suggest a single antibody. I'll show you an example of that in just a moment. If you have variable reactions, in other words, if you have some that are 2+ and some that are 1+ and some that are 0, that suggests generally either multiple antibodies, especially if you've got a wide disparity such as 4+ and 1+. I didn't mean to make light of that earlier. If you've got wide disparity, that certainly suggests multiple antibodies, but you should also keep in mind that a single antibody showing the dosage effect, that double dose versus single dose thing I mentioned earlier, those can also show significant variability in terms of their reactions. Now, in terms of the number of cells that are reactive, again, let's assume that we have a negative autocontrol. If you have a mixture of reactive cells and non-reactive cells, that suggests either a single alloantibody or potentially multiple alloantibodies. Obviously, that would also depend on the variability. But if you've just got some that are positive, some that are negative, it could be one or the other. If you only have one reactive cell, that suggests a single alloantibody against a low prevalence antigen. While if you have virtually all cells reactive, that suggests either multiple allos or a single allo against a high prevalence antigen. I'll show you that graphically in just a second. Now, in terms of the phases where antibodies tend to react, let me take you through this. Please understand that what I'm about to tell you are general rules, and they're not universally going to be true, but you can usually rely on these for the most part. Okay, when we look at the Rh blood group system, what we see is that antibodies against Rh antigens have a particular characteristic. They tend to react not only at the anti-human globulin phase, but they will also, on liquid panels obviously, react very commonly at 37 degrees. That's a little unusual. Most so-called quote-unquote warm antibodies, those that react best at the anti-human globulin phase, don't necessarily have 37-degree activity. So you see 37-degree activity without immediate spin activity, you really should be thinking of possibility of something in the Rh system. On the other hand, the main other clinically significant antibodies, your Kell system antibodies, Duffy system, Kidd system, MNS system antibodies, those all tend to react best and in many cases only at the AHG phase. Now, I should be really clear on this. It is absolutely possible for any of these that I've described so far, RHs and the other ones, to react at immediate spin or 37, but typically that only occurs when they are brand new antibodies. In other words, when the antibodies are just forming and they're in development and they have a significant IgM component, those IgM antibodies can react at immediate spin in 37. But in general, mature antibodies will react in the ways that I'm showing you here. You got some variable ones, your XGs and your Lutherans, and honestly, we don't pay a lot of attention to those. And then finally, you have your antibodies that many people will call cold antibodies, and I will admit that I will many times call them cold antibodies myself. The truth is that these are room temperature antibodies. They react at immediate spin. They may react at 37 degrees as well, but they react best at immediate spin. And those antibodies are the Lewis antibodies, Lewis A, Lewis B, the N, and the P antibodies. It's almost alphabetical, isn't it? L, E, M, N, and P. Now, I have to say one thing before I move off of this slide to those of you that are more experienced in immunohematology. You've probably looked at this panel where it says MNSS, and you've turned up your nose and you've said, oh, that's just gross, because it's actually the MNS system, not the MNSS system. And you're right, but get over yourself a little bit, okay? I'm sorry. I just haven't had a chance to change this, and you're going to see that throughout. So my apologies in advance to those of you immunohematologists, and I'm obviously poking fun. I hope you guys don't think I'm serious. It makes me laugh, but it's not that big a deal. All right, so let's look at the next slide. And the next slide talks about, it characterizes some of the things that we talked about before and kind of brings them together. We're going to spend our time today talking about two different scenarios. The uniform reactions, both warm and cold, where you have positive and negative cells. Those are typically either single or multiple IgG or IgM alloantibodies. So we'll spend a lot of time talking about those. In addition, on the variable reactions, we'll spend our time talking about specifically reactions that are both warm and cold, and where you have many or most of the cells being positive, and you're looking at multiple IgG and IgM alloantibodies. Again, there's going to be more on this whole separation as we do future podcasts, but for now, those are the general areas on which we are going to focus. And let's just give you an example of that. Let's go back to the panel that I told you we were going to kick around for a while, and this is the one that we already looked at, the autocontrol. Now we're going to take a look at the general pattern, and what do we see? Well, here's what we see. We see an unlabeled column of reactions, only one column, so that tells you that it is most likely, since it's unlabeled, most likely either gel or solid phase. The lack of the positive and negative control thing at the bottom says that it's probably gel. Again, we might be wrong, but we're just trying to learn all we can from someone else's work, basically. Someone else has done this panel, and we're trying to learn all we can. Okay, so number two, we look at the autocontrol, and we see that that's negative, so there's no obvious autoantibody. Great. The third thing, let's take a look at the pattern. So every place where there's positivity, the reactions are 3+. That's cells 1, 2, 3, 4, and 11, and the others are completely negative. So I think you would agree with me that this is a completely uniform pattern, and as a result, a single antibody is most likely. Since this is AHG phase, we're assuming that it's a single quote-unquote warm antibody, so that narrows things down a little bit, but more on that as we go through. Okay, so now that we've looked at the general pattern, we have a basic idea where we're going. Let's look at what's not there. That may seem a little counterintuitive. Some of you may be used to saying, okay, well, I've seen kind of what's there. Now let me try and fit something together. I really would advise you against that. In my opinion, the best way to do these things, and the way I was taught, is to look at what is not there. Let's do crossouts. And here's how you do crossouts. So we look at our panel once again, and we notice that there are cells 5 through 10 which are completely stone cold negative, no reaction whatsoever. Now, some people will actually physically highlight those cells all the way across the panel, like I'm going to show you right now. Honestly, most people don't do that, but it certainly can be done. But the important take-home message is that you are going to focus on those cells first, those stone cold negative cells, to try and see what you can learn from them. The basic principle is, if an antigen is there and there's no reaction, then that antigen is likely not the target of your antibody. Let me show you that up a little closer. So here's one of the ways that we do this. These are the crossouts, and when we do crossouts, again, we focus on the completely negative cells. So we're not going to look at the third cell on this particular tiny little portion of a panel. Again, notice this is a totally different case than what we had on the panel that was just up. We have immediate spin, 37, and IAT reactions, and we're just looking at the Duffy A and Duffy B, FYA and FYB reactions. Okay, so let's look at cell 1 here, which is the first of those two completely negative reactions. Let's look at cell 1, no reaction whatsoever. We have what we assume it to be a double dose of FYA antigen. Again, we talked about the caveat before. It may not be, but we're going to assume that it is. And as a result, since the antigen is present, it's a double dose, and there's no reaction, we're going to put a single slash through the FYA antigen up at the top of the panel. Now, many people will put those slashes through down at the bottom of the panel or in the cell where I have the plus sign circled. I personally don't care for that, but many people like that and will do it that way as well. Let's move on to cell 2. Cell 2, as you see, is completely unreactive again. However, if you look at what we have in terms of the Duffy phenotype here, it's clear that this particular red cell has a single dose of both FYA and FYB antigens. As a result, you should not, unless it's completely unavoidable, you should not do any rule outs based on that. Now, I will tell you that some people will put kind of a horizontal slash through the FYB and FYA there to indicate that they've done a so-called single dose, or some people say heterozygous rule out or cross out. I personally don't do that because I like the slashes that I see to indicate a homozygous rule out. I said it, a double dose rule out. But again, some people will do that. If you see a horizontal slash, that's what that means. Okay, so with that being said, let's go back to the big panel and let's kind of walk through this and let's see exactly how we do it. Okay, so the method that I'm about to show you is the method that I use. Actually, I'll first show you the method that you were probably taught if you've learned this before, and it's the most common method that is taught, and it's great. It works wonderfully. Let me show you how it works. So you look first at the first completely negative cell, in this case that's cell 5, and then you either take a piece of paper or a straight edge or a ruler or something of the sort, and you slide it up until you've got a sharp edge there, and you're going to look just at those reactions for cell 5. And generally speaking, what you're going to do is you're going to go blood group by blood group or paired antigen by paired antigen. In this case, we're going to look at Lewis A and Lewis B together because those are paired antigens. All right, so when we look at Lewis A, we see that in cell 5, we have a double dose. We're assuming a double dose of Lewis A. So as a result, we come in and we take our pen or pencil and we do a single slash through Lewis A. Great, no problem. So we're done with that. Let's move on to the next pair, which is the big S and little s pair. And we do the same thing. We see that big S has a double dose. There's no reaction. So again, pen comes over, write a single slash through the big S. So easy, no problem. Those slashes indicate a double dose rule out. You go along, you do the same thing with M and N. Again, in this case, you see that the M has a single rule out, a double dose rule out. You go along, you do the rest of the panel exactly the same. I should make mention of one thing. I talked about how you don't want to do crossouts based on single doses of the antigens. That is really true across the board. It's especially true for blood groups that show dosage, such as Duffy and KID. It's somewhat true in RH as well. But in general, the only one that people consider relatively acceptable to do a cross-off on when you don't have a double dose is big K. So big K is a hugely important antigen. It's really, really rare to find big K positive, little k negative cells. Most panels won't have those. So most immunohematologists are okay with doing that single dose rule out with a big K. I'm not going to show you that right now, but just wanted to let you know that. Okay, so you've finished with cell 5. Now we want to move on and look at the next negative one, which is cell 6. And guess what we do? We do the exact same thing. Okay, look in cell 6. We go pair by pair. We've got Lewis A, Lewis B. Again, this is a double dose Lewis A. You put a single slash through the Lewis A. I will tell you that some people, once they have a single double dose rule out, won't put any more slashes, and it actually will save them time looking at the panel. Little trick for examinations, I always do that on examinations, and in some cases I do it in real life as well. But the way that I was taught and the way I'm showing you on this particular panel is to get at least two, to try and get at least 2 double dose rule outs before you stop doing your slashes. Okay, so let's move on to the next pair, which is big S and little s again. Again, here we have single doses of both big S and little s, so you would not do any rule outs or any cross outs on either one. There, move on to M and N as the next pair. Here we have assume assumed double dose of N, and we put a single slash through N, and guess what happens? We move along and we do the same thing all the way down the panel, moving on down through each and every cell and looking at each and every cell. That works great. And honestly, you do that and you'll be golden. You won't have any problems whatsoever. I will tell you, I personally do these with a slightly different approach. I actually, rather than doing things horizontally, I look at things vertically. I look at things blood group by blood group. So in other words, my piece of paper or my straight edge or ruler comes from the side, and I look at things again blood group by blood group. And there's a couple of ways that you can do this. Let me show you the way that I typically do it. So here, okay, again, here's cell 5. Here's Lewis A. We assume double dose, put a single slash. Move down to cell 6. Uh-oh, again, another double dose, no reaction. Move our pen over, take another slash through Lewis A. Now, basically, I don't have to look at any more Lewis A's for the rest of the panel. I don't have to look at 7, 8, 9, and 10, no matter what they show, because I've already got 2 solid rule outs. Again, some people just take 1 to do that, and that's totally fine. Moving on to cell 7, again, you can see the same sort of thing. A double dose Lewis B, put a single slash, move on down to cell 9 where you have another one and put another slash. Again, that's the way that I typically do it. However, if I'm rushed or if I'm on an exam, and again, the way many people do it is they'll look at it like this. Let's look at that. Let's start from the beginning again. So here we have Lewis A, double dose, single cross out, good, I'm done. I'm not looking at Lewis A again. I move down, find the first Lewis B that's double dose, I put another slash, great, I'm done, I'm moving on, I'm not looking at Lewis anymore. So that's absolutely acceptable as long as you understand that doesn't completely rule out the antibody, and you may have some more work to do down the line. We'll talk about that in a minute. Okay, either way you do it, you move on to your next pair, which is big S and little s, and you do the same kind of thing. You do your, in cell 5, a double dose rule out for big S, cell 6, no rule out because it's heterozygous, cell 7, another double dose rule out for big S, cell, excuse me, cell 8 we don't need to look at because we already did the rule out. Cell 9 is heterozygous or single dose, and cell 10 is finally a double dose rule out for little s, so we put a single slash through little s. Okay, so you do this and you go blood group by blood group, remembering the big K exception for the single dose rule out, and you go across and you end up at the end with something that looks like this. So you've got many antigens that have been ruled out as the target of your antibody, and you've got many that aren't, that haven't been already. So what most people will do is they'll go through and they'll put circles around everything that has not been ruled out. So, excuse me. More on that in just a moment. So now that we've done that, now that we've seen what's not there, the next thing to do on our system is to look at what is there. And let's try and do we've done some cross outs, let's try and do some rule ins based on the pattern of what we're observing. The first thing I always try to do is I try first for a single antibody to explain all the reactions. That's just my basic starting point. I always want to try for one antibody to explain all the reactions. Okay, let's go back to the panel that we've already showed you and that we've already done our basic work on. And now instead of looking at the yellow highlighted cells, we're going to look at the pink highlighted cells. Again, most people don't actually highlight them this way, but in your brain, these are the ones that you're going to want to look at. So what we see in those cells is as we saw before, a uniform reaction. You see that on the right with 3+ reactions every place where we have reactions. So again, this tells you right away we probably have a single antibody. So what we want to do at that point is we want to, again, either in your brain or just looking at it, I generally will write down which antibodies are possibilities or which antigens are possible targets of our antibody. And here you see them up at the top right of the screen. Let's take those one by one. Let's look first at the D, the big D antigen. Well, where do we have big D? Well, that's pretty obvious. Every place we have a reaction, we have the presence of a big D antigen. So that would absolutely fit as a single antibody explaining all the reactions. So I would circle big D. I certainly wouldn't rule it out. In fact, I would think that this is probably going to be an anti-big D. But let's not ignore the other possibilities. Let's move on and look at look at anti-big C. Is that a possibility? So here's anti-big C, or here's the C antigen, I should say. Let's look down the column and see where it's present on which cells. Well, it certainly wouldn't work as a sole antibody, would it? Because it doesn't explain the positive reactions in cell 3 and 4. It's odd that there's no reaction in cell 5 when big C is present. You could make the argument that is a single dose big C, and you'd be correct because there's a little C there as well in cell 5. But it certainly wouldn't work as a single specificity. So what I would do is I would at least preliminarily say it's probably not big C by itself. Okay, great. Let's move on and let's look next at big E. Is big E a possibility? Again, where is it present? It's only there in 2 cells. Again, certainly wouldn't explain every reaction, and there's no reaction in one place where it's present. So it's probably not big E. Okay, with that being said, now we're on to a group of cells that everybody wonders about. So we've got our antigens that everybody wonders about. We've got things like CW, which can be more present, but you've got V and KPA and JSA and Lutheran A, all of which are very uncommonly even present on an antibody panel. And you're not going to be able to rule them out on most antibody panels because there's nothing there present to do rule outs with or cross outs with. In general, what I tell people about this is don't worry about it. And I know that sounds cavalier and weird, and it's those of you that are in blood banking are gasping right now, but that's okay. You really don't need to worry about them. For the most part, these antigens are not the targets of antibodies. It would be really uncommon to find these as an issue. And more importantly, if one were an issue, and you were doing a major cross-match, a full cross-match, you would actually pick it up if the antigen happened to be there. So again, not that big a deal, and I really don't spend a lot of time. I don't spend any time worrying about those cells that have very rare antigens. CW again is kind of on the borderline. I think about it, but I think less about it than I do many of the other major antibody specificities. So in this case, I think what we can say is, based on everything that we've seen so far, this looks like an anti-D, and we can make a preliminary identification of a single anti-D that explains all the reactions. We're not done in the real world, but on the exam world, that's certainly a reasonable conclusion to make. Okay, so after we've tried first for a single antibody, if that doesn't work, failing that, well, the first thing that I generally try to do is, depending on what the pattern looks like, is that I'll hypothesize 2 antibodies in the same phase. Let me show you what I mean by that. This is another panel. This is a different panel, though it looks similar at first. And let's see what we can learn just by looking at it. So let's look at the reactions again, unlabeled, single column of reactions. We say again, it's probably gel or solid phase, most likely gel. The autocontrol is negative, so there's no obvious autoantibody. And let's look at the reactions themselves. There is a lot more variability in this one than we saw in the first panel. We've got 4 pluses, 3 pluses, and 2 pluses. And that in general suggests one of 2 things. Either you have multiple antibodies or you have a single antibody that's showing dosage. So what I try to postulate is, you always try and fit one. If that doesn't work, let's see if we can fit more than one. Okay, so there's our reactions that we've already looked at. Well, what does this tell us? Again, variable pattern, multiple antibodies are most likely. We do the same thing that we did before. We go through, we look at the negative cells, we do our crossouts, and we get a pattern that we see up at the top that looks very similar to the last panel that we looked at. In fact, when you generate your list, the list looks exactly the same as the other ones, as the other panels did. Okay, so you may be thinking, well, this looks like another D, right? Because we saw the anti-D on the first one. Well, maybe not quite, because if you take a glance at this, here's the places where D is present, and we've got reactions in every one of them. However, we can't explain the reactions in cell 5 with an anti-D. So cell 5 has additional reactions, and what you find is, again, we don't have a lot to look at because we're ignoring V, KPA, JSA, and Lutheran A. We've ruled out everything else except for big D, big C, and big E. CW is, weird. So let's see what we need to do to fit that pattern. Well, D doesn't explain it by itself, obviously. Does C explain it by itself? No, but if you add those 2 together, you see you've accounted for every single reaction. Now, the big E I haven't highlighted, but it doesn't seem to add anything. In other words, it doesn't make that D in cell 3 stronger when the big E is there. So that's probably not anti-big E. Again, you've got more work to do, and we'll talk about that in a minute, but this is preliminarily the combination of anti-big D and anti-big C. Okay, so if that doesn't work, what do you do? Well, if you can't fit two antibodies in the same phase, again, depending on the pattern, you may need to go to hypothesizing one warm and one cold antibody. Let me show you how that looks. This is another panel, obviously a different panel. This is tube testing. You can tell that by the fact that we've got immediate spin, 37, and IAT phases. No question about that. The autocontrol is negative. Great news. We don't have an autoantibody. But now let's look at the pattern. This is a really odd pattern, and again, if we're trying to hypothesize first a single antibody, I think you'd have a hard time, because what we have in cells 7 and 11 is a fairly strong reaction at the AHG phase. In cells 6 and 10, we've got across the board 1+ positivity in all three phases. That doesn't add up with the other one. In cell 8, you've got purely immediate spin and 37 reactions with a negative AHG. And in cell 5, you've got, weak at immediate spin and strong at IAT. You look at a pattern like this, it's abundantly clear that this pattern is variable. It's abundantly clear that there's no way one antibody could do this, and it's abundantly clear that you have at least one warm antibody, not autoantibody, one warm antibody and one cold antibody. Okay, I hope that makes sense to you, and as you look at that you could see that. So how do we approach panels like this? Well, honestly, like I said, I tend to approach things the same way as often as I can, and here's how I do it. I first look at the completely negative cells, and I do all the crossouts that I can based on those completely negative cells. Again, if you look up at the top, you can see I've ruled out a lot of potential specificities for this pair, most likely at least pair of antibodies. What I will do next, and you'll see some variation on this, but I typically will look at the cells which have reactivity at AHG. And that would be cells 5 through 7 and cells 10 and 11. Other people will only look at the strong reactions at IAT or AHG, and that's okay too. I tend to look at all of them and see if I can fit anything based on that. So I will look at the antibody specificities that I know tend to react at AHG, and we already talked about that at the beginning. We also mentioned that the cold reacting ones, the ones that react best at immediate spin, are these up at the top left: Lewis A, Lewis B, M, N, and P. So it's probably not any of those reacting at AHG. So all we have left, if you ignore the KPAs and JSAs and stuff, you're left basically with Duffy B, FYB, and JKB as those potential quote-unquote warm antibody specificities. And let's see if either one of those fits perfectly. Let's look at Duffy B first. Well, as you can see, every place Duffy B is present, you have at least somewhat of an AHG reaction. And in fact, in the places where Duffy B has a single dose, the AHG reaction is weaker, such as in cell 6 and in cell 10. And the places where there is a double dose of Duffy B, again, a presumed double dose of Duffy B, the reactions are stronger. So the Duffy B certainly works. Let's look at JKB on the other hand. Obviously, you've got that straggler sitting up there in cell 2. Yeah, but dosage, you maybe could ignore that. But what you can't ignore is looking down in cells 10 or 11, and you can see why JKB does not fit as the warm specificity. If you look, you see that both cells 10 and 11 are single dose JKB red cells, and look at the difference in the IAT and the AHG reactions on the far right. You have 1+ in cell 10 and 3+ in cell 11. So it doesn't make sense that both cells being single dosed would give you that much variety in the IAT reaction. So what we can say at this point is that this is most likely an anti-Duffy B for the warm reacting antibody. Okay, well now let's look at something different. Let's look at the quote-unquote cold reactions, or in this case, the room temperature reactions. Those that are reacting at immediate spin, maybe with 37, and I've highlighted those in blue. And again, if we're only looking at Lewis A, Lewis B, M, N, and P, you look up at the top row, we've already ruled all of those out except for Lewis A. So let's see if Lewis A fits. And it does. It's a perfect fit, explains all the reactions, does everything you would expect it to. And so again, you make a preliminary identification for this panel of the combination of Duffy B and Lewis A. Great. All right, so if that doesn't work, then we're in trouble. And honestly, if that doesn't work, we're in a situation where we're going beyond what we want to do in this podcast today. And again, we'll do this in the future, but then you have to start thinking about multiple warm antibodies, multiple cold antibodies, and we're going to get into that, but we're not going to do it today. That'll be in a future podcast. Okay, so we've done everything. We've looked at what is there. We've made our preliminary identifications. Sometimes you have to go further. Sometimes you have to use some special techniques to try and sort things out. And let me talk to you about some of them. One of them I've already mentioned, and some would say that this is not some as necessary thing to do, but that phenotyping is essential to confirm the identification of an alloantibody by demonstrating that the patient doesn't have that antigen. In other words, if it's an alloantibody, it's against someone else's, not yourself, antigens. So if you phenotype negative for that antigen, that helps confirm the specificity of the antibody. But it is just a tool, and it is not the sole measure of confirmation. You've seen this panel before. This is the one that we looked at earlier that had the combination of anti-Big D and anti-Big C. And if you look down at the bottom left of the panel, you see a couple of reactions here where we have phenotyped this particular patient for both Big D and Big C. Now, the reality is you're not going to have to phenotype the patient for Big D. I'm just using this as an illustration. Obviously, we know whether someone's Rh negative or Rh positive, but I just, again, show it to you as an illustration. More importantly, the person is Big C negative, so again, that helps to confirm your preliminary identification of anti-Big D and anti-Big C. Adsorption is another special technique that can sometimes be used. That's basically the technique of removing antibodies from a sample by incubation with antigen-positive red cells. It can be done either to remove autoantibodies or alloantibodies. Let me show you how that works. There'll be more on this later, but autoadsorption, let's say we have an autoantibody, and that autoantibody is reacting against so many cells that we can't see that there's an underlying anti-Big K. So in order to find that Big K, we have to somehow get that autoantibody out of there. And the way that we do that is by incubating with the patient's own cells, which are obviously the patient's own cells. So we would assume if that anti-Big K is there, that they're Big K negative. You incubate those cells together, and basically the patient's own cells kind of soak up the autoantibody. You may have to do it multiple times. It soaks up the autoantibody, and what's left behind in the adsorbed serum, the serum that's left behind after an adsorption, in this case, it reveals, oh wow, I do have an anti-Big K there, and you're able to confirm that and do your testing. Alloadsorption, on the other hand, is the same kind of deal. Let's imagine that we have someone with multiple alloantibodies, like this combination of anti-Big K, anti-Big C, and anti-Big S. In that case, if you say you were pretty sure that you had identified already the anti-Big K and the anti-Big C, and you thought there might be an anti-Big S there, well, one of the things that you can do is you can find cells that are positive for the first two, positive for Big K and positive for Big C, incubate them with that serum sample, and those cells would soak up the anti-Big K and anti-Big C antibodies and leave you behind with anti-Big S, so that you could obviously test that adsorbed serum, and you could show that that anti-Big S clearly is there. Now, Ellucian basically takes cells such as those that were used in an adsorption. It doesn't have to be, though. It can just be cells coming straight out of the body. And Ellucian separates the antibody from the surface of the red cell. So you treat those red cells either with temperature variations like heat and cold, freezing, for example, or with chemical treatment. Commonly, glycine solutions are used. And what you have left behind is basically the antibodies in solution and potentially red cells left behind. Many of these treatments are toxic enough that you may not actually see residual red cells. We may burn them up in the process. But either way, your desire is to see that eluate at the end that has the anti-Big K and Big C in this particular case. Finally, proteolytic enzymes. We've talked about this in both of the preceding podcasts, but let me show you this illustration again because I really like it. Enzymes like physin and papain cleave proteins. They're proteolytic. And so they can change the antigen, how the antigens are expressed or how the antibodies bind. And again, just an example of this. Red cells have a forest of antigens on their surface, including things like glycophorin A and glycophorin B. This is showing glycophorin A, obviously, in a stylized format, which carries the M antigen. Well, if you throw a proteolytic enzyme in, take a guess what happens. This Pac-Man comes along and chews up some of these glycophorin A's, and you have decreased expression of the M antigen. In fact, you may have completely eliminated your M antigen expression. Now, this can also have a different effect. In other words, if you have a red cell protein or antigen that's present closer to the surface of the cell, if you clear off some of the forest above in the way that I just showed you, then antibodies may be able to bind to them better. And again, we've talked about this ad nauseum, that the blood groups that do better after enzymes, or you get better reactions after enzymes, include things in the ABO family, as well as Rh and KID antigens. And obviously, M and N antigens are damaged by enzymes, as well as Duffy antigens, which can be completely destroyed. Okay, the last thing that you have to do is to ensure statistical significance. After we've done all our work and we've gotten our answer and we think, yep, this is what it is, we've got some more work to do in many cases in the real world. And what that means is that you want to make sure that what you're seeing is not just pure chance. Traditionally, the traditional interpretation of the statistical relevance of this is that in order to say that this is the antigen, this is the target antigen here, you have to have 3 positive reactions with the patient's serum when the antigen is present, and 3 negative reactions when the antigen is absent. However, the standards for reference laboratories that you see listed there only requires 2 of each reaction to assign specificity. So different laboratories will take different approaches, and I'm not going to argue either way about it. Either way, you have to do your best to ensure statistical significance. Bottom line for me is that for practical purposes, if you're doing these, even in the real world, but absolutely on a test, preliminarily IDing only requires 1 double dose rule out to establish lack of identity. It doesn't mean in the real world your work is done. You have to do additional cells to rule in or rule out specific antibodies. And here's an example of that. You've seen this panel before as well. And this panel was one, I beg your pardon, this is actually the first panel where we had an anti-D, but we don't necessarily know that we don't have some of the other ones. In other words, we haven't achieved a level of certainty with AntiBig C because we've only got one situation where AntiBig C is there and we have no reaction. And the same thing is true with AntiBig E. So you've got more work to do. You would choose some selected cells and you would do that work and finish it up. So basically the bottom line is that in order to do this, in order to learn it, you have to do some. So the next podcast will take at least 6 cases, go through them. I'll walk you through them. We'll do them together and we'll figure out exactly how to do them, show you some of the tricks of the trade, and hopefully it'll be a nice learning experience. I do want to say very clearly that I've had so much help making this podcast. I'm enormously grateful to Monica Lassar at the Bonfils Blood Center Reference Lab, to Dr. Tuan Lei, and to Cami and Colleen also at the Bonfils Reference Lab, as well as to the fabulous Kevin Ellman at North Colorado Medical Center in Greeley, Colorado, who assisted with cases. Finally, a big shout out to my mentor in immunohematology, who may not even remember me, but her name is Connie Howard. She has worked for years at Walter Reed Army Medical Center. She's the best, and she taught me most of what I know, and I'm really grateful to her. So that's it. We will roll along and get together the next time. I want to make sure that that you guys have every opportunity to learn this as best you can. I hope you've enjoyed it. I hope you've had a good time. It's been fun for me. We'll talk to you next time.